Hey, welcome to our notes for continuity and end behavior. And before we start looking in example 1 at what it means for functions to be continuous or discontinuous, I'd like you to ask yourself, if watching a movie in a theater is continuous, why is watching a show on TV discontinuous? And if you think about the difference is there, watching a movie in a theater, you see the entire story from beginning to end without any breaks. But when you watch a show on TV, there are breaks in the story by episode and also from commercials. So those interruptions by the commercial breaks or the gaps between episodes, those are pieces of time where the story isn't being told. And that would be an example of a discontinuous show or a discontinuity in the story. Okay, when you look at functions, a continuous function is defined over all the real numbers. So for any point A along the real numbers, there's going to be an output f of a y value for that input of a. Okay, if there's a place where a is undefined on the graph, then that would be considered a discontinuous function. So for example, here we have a hole in the graph at A. Okay, that means that it's undefined here, right? I can't use A in the function because there is no f of A at A, and that hole in the graph is referred to as a removable discontinuity. When you get to calculus and you study limits, you'll find out that it's removable because you can plug that hole. But for pre-calc, we're just classifying these. So we want to know that a hole in the graph is a removable discontinuity. Okay, in the next graph, we can see this piecewise function where f of a is defined at this closed endpoint, but it's undefined at the open endpoint above it. Okay, and that's called a jump discontinuity. Okay, in the next example, we have a fixed endpoint here. So the graph is defined at f of a, but if I was to put my a over here, there's nothing there, right? So this is not continuous over all real numbers. It's continuous over its domain, but not all real numbers, and so we call that endpoint discontinuity. And that occurs because f of a exists but can't be approached from both sides, right? At this endpoint, I can get there from the left side of the function, but there is no function on the right that I can approach a from the right side. Okay, then our last example is a rational function, and we see this vertical asymptote here at a, and that's causing something called an infinite discontinuity. So the graph is approaching a from the left, but it bends up and it goes right alongside a, closer, 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 always to that vertical asymptote, but it never ever gets there. So the y value is approaching positive infinity, but it can't ever actually equal a. And the y value coming from the right side, the same thing is happening. It's getting closer, closer, closer to a, but it never equals a, it never touches a, and the y value instead is extending down to negative infinity. So we refer to that as an infinite discontinuity. Okay, so in example 1, we have 8 graphs here. We're going to do the first 4 together. And in example A, we have a polynomial here that is continuous over all real numbers, right? It's defined over the set of all real numbers. There are no breaks, no holes, and no gaps in this function. So we call that continuous. A continuous function over the real numbers means we could start at negative infinity and trace that curve the whole way up to positive infinity and never have to lift the pencil, right? That would be a continuous function. Okay, B is discontinuous because as I'm tracing it, I have to hit this hole and lift my pencil and hop over that hole because it's undefined there and then continue on. So we call that a removable discontinuity. In example C, as I'm tracing this rational function, this hyperbola, starting at negative infinity, I get here at this vertical asymptote at 2, and I can't get to the other side without lifting my pencil and going across, hopping over that asymptote, and so that is an infinite discontinuity. Okay, then in D, I can't even start tracing this curve at negative infinity because there is no function there. It's not even defined until I reach this endpoint. And so we call that an endpoint discontinuity. So go ahead and pause the video and try E, F, G, and H on your own. You want to label these as continuous or discontinuous, and if discontinuous, identify the type of discontinuity, and then when you're ready to resume, we'll check your answers. Okay, so in example E, this is a square root function, and that would be an endpoint discontinuity. Okay, example F, this is the parent graph of the floor function, and if you recall when we learned about parent graphs, the floor function rounds whatever decimal value is inside down to the nearest whole integer. Unless it is an integer already, then it stays the same. So the floor of 0 is 0, so there's a closed circle here at the origin. The floor of 1/2 is also 0. The floor of 0.9999 is also 0. But the floor of 1 is 1. And so there's a closed circle up here at 1, 1, which means 1, 0 has to be open. And that's how we get this pattern of horizontal line segments that have closed circles on the left side and open circles on the right side. Okay, that would be an example of a jump discontinuity. Okay, G is another polynomial that we can trace from negative infinity to positive infinity without lifting the pencil, so that would be a continuous function. H is a rational function being shaped by this vertical asymptote here along the positive x-axis, and that's an example of an infinite discontinuity.